Okay, so in this session today, actually, we change a bit the program. I was thinking first to do what is called dynamical system analysis, but finally we will do that tomorrow, because tomorrow the time is a bit shortened. So we are just going to do the calculations for Mathematica of what we did so far, which means how to calculate, and then if Sushant has time to come back because he has a meeting, we will see how to do that with Maple. So if you have a computer, you can go at the same time. The idea is the following, is that how do we calculate all what we did? Christoffel symbols, Riemann, Ricci, curvature scala, etc. with Mathematica, with some program that we just made by ourselves. So the first thing that you have to do, so I will do it at the same time than you. Let me just open an additional Mathematica file. I put that I will work in 4 dimensions, and thus you do a right-hand side click, and you choose Insert Table of or Matrix, and you choose Matrix here, and you take a 4x4 matrix. So then you have a matrix that I will call GG, which is going to be my metric. And I can fill it with the metric I want. And today I'm just going to take just this actually standard metric, which is the Friedman universe. So you just define the matrix, and that matrix will be our metric. So this is a program that you do by yourself. You don't need anything more complicated than that. Okay, so that is our metric. But now, what we have to say is that we have to add additional things. So at the same time, I will comment here. So the idea is the following. We have a matrix that I call GG. So this is my matrix, but what I want is to put indices. So I want to define the metric G index mu nu equal to things. So for that, what I have to do is that I will call something which is going to be called G down. G down will be for lower indices, mu nu equal to the terms here. So for example, I will say that G down 0, 0 will be this matrix which is the 1, 1 term here. Mathematica does not start from 0. Mathematica starts from 1. This is 1, 1. It's not 0, 0 for Mathematica. So I have to write it in this way. For us, we call it 0, 0. So you have to be careful on that. So that is the second step. What I'm going to write is something like that. Let me first erase that. That G down ij is the matrix here, and I took it on the position I plus 1, j plus 1, because as we said, Mathematica starts from 1 and not from 0. But of course, I have to make a loop on iij to say that I will put 0, 0, etc., all the terms. So I just put a 4 for the loop, and it will be something like that. I'm going from j equal to 0 to the dimension, which is 4, so from 0 to 3. This means that every time I increment by 1, I do the same with I, and I'm getting this. So let me run the first part. Let me run the second part. So if I say what is g down, now 0, 0, it will tell me it's -1. If I say what is g down 1, 1, it should say that it's a squared. G down 1, 0, it's 0, etc. So then it works perfectly fine. Okay, so that is the first part, is just to get indices, the lower indices. So G down will be the metric that I will use. Now I want G with upper indices. So what is with upper indices? I have to find the inverse of the matrix GG and then put the indices I want. But first I have to take the inverse of it. If I take the inverse of it, then I have the indices which are up. So this matrix, I will call it G up for indices up of equal to the inverse of the matrix GG, and I will take it at the same position. Oh, by the way, I don't know if you have questions or not, because I'm just going, but for example, this part here, in Mathematica, to put it twice, what you can do is even better. You click on escape, then you put twice like that, and again escape. So it might put it like this sign, which means twice actually. Tac, tac, escape, twice, escape. But this is, I don't know how you call it escape also? Yes. The button, top left, it's escape, yeah. So it is -1.
Sir, I want to disturb you for a minute.
It doesn't work.
Just stay there.
Okay, sure. So,
Sir, just a minute.
okay.
आप सबको दिख रहा है? आप थोड़ा सा डार्क इसलिए किया है कि कैमरे में कुछ नहीं आ रहा है. Sir, go ahead.
Okay, so it's good for camera, but is it good for you? So you can see the video after. Okay, so it will become even darker. No. So this is the way Mathematica tells you I'm taking the 1, 1 part. You have to put a double square bracket. So either you write it like this, or you write it with escape, escape, which makes it a bit more compact. But you see that it's exactly the same thing. Just to learn a bit about escape, that if you want to write some Greek letter in Mathematica, alpha, for example, you click on escape, alpha, or A, escape, and it gives an alpha. Escape, B, escape is beta, etc., etc. So with Mathematica, it's very simple to write indices. You just have to write with escape something, and then you get actually, you get the Greek letter. Okay, so questions so far? For the ones which do have a computer, did you manage to write this first part? Yes? Okay. So,
Sir?
yes?
So right now we are just making computer to read this and write this.
Yes, exactly. So the GG here is reading the terms which are in the matrix. So the inverse, I'm doing exactly the same structure in the sense that I'm saying first you do let me just first show what inverse gives. inverse of G gives this. If I want to put it in a matrix form, because if you wanted to look at it better, so you see this is the inverse of the matrix we had before. So first I take the inverse, and then I put the indices. We know that Mathematica starts from 1 and not 0, so there is this shift of 1. And the same way, I'm just making a loop, and that's it. And now I have G up, which means with indices up. G up 0, 0 will be minus 1, of course. G up 1, 1 will be 1 over a squared. So with that, I define completely now so you can define any metric, and I have first thing, which is the most fundamental thing, the metric. If I take, for example, a Schwarzschild kind of metric, I just define my metric in this way. And theta, I write escape, and I write really theta. And then escape again. And then I'm getting it. So with that, I have the Schwarzschild metric. I can run it, calculate this, and I will have the metric, for example, G up 1, 1, which is something, but if I simplify it, it will be just the inverse of this. Okay. So with that, I have the metric. So now, the next step, once we have the metric, is to calculate the Christoffel symbols. So let me rewrite the formula of the Christoffel symbol. Now, but before that, I have to say what are the coordinates. Because I have to make derivations, so I have to say that x0 is time, x1 is x, etc. So I will do something which is, I will put them as rules. This is what I did. It doesn't mean that this is the smartest way, but this is the only way I found to do it. I did something like that. So I will go back to Friedman universe. The good thing is that if you do your program by yourself, is that you can generalize it to anything. So you can work it out, this for any type of model. And these are going to be some sort of rules. R1, every time I say I want R1, means that I say that x0 is t. x1 is x, x2 is y, and x3 is z. These are the coordinates that we want to use later on. So I'm just saying that I will say that x0 is t, x1 is x, x2 is y, and x3 is z. So now I can write the gamma. The gamma, this is the definition of gamma. It's 1/2 G rho sigma d mu G nu sigma plus d nu G sigma mu minus d sigma G mu. For the people who don't know very well with that, when we have an index which is repeated, it means that we have a summation. That is what it means. So we have a summation here from sigma equal to 0 to 3 of that. So now this I can write it easily. So I will just say that I want 1/2 of G up index rho sigma and parenthesis, I will put a derivative. A derivative in Mathematica is like that, of G down, index nu sigma, and I will derive it with respect to x mu. And I will say that to Mathematica that they should know the rules I put before. Okay, so what does it mean, this structure? Here I say that you do the derivative of G down nu sigma, as it is written there, the derivative with respect to x mu, but you should know, that means that you should know, means knowing that R1, R2, R3, R4. So every time that the system will get x0, it will know that x0 is time. Every time that there is x2, it will know that x2 is y. So it will make the derivative knowing what is x mu, because otherwise it will not know what is this coordinate. So you have to put that slash dot R1, slash dot R2, etc. If you do it in this way, it will know what is the derivative. Let me just maybe isolate it first and make an example. So if I want to do the derivative of the 1, 1 component, and I want to do the derivative with respect to I don't know, x1, to x, or to time, because otherwise it doesn't work. So here the system understands G down 1, 1 is a squared. You derive it with respect to x0, and the system knows that x0 is time. So if you derive a squared with respect to time, you get 2a dot. So then you know exactly which derivative you are doing. If you don't put that, then it just makes a derivative with respect to some variable x0, but Mathematica doesn't know what is x0. So it will just give 0. So every time you have to write what does it mean, actually, these components. So then I just continue writing this plus the full gamma. So there was 1 plus, 1 minus. The plus, the indices are sigma mu. Derivative with respect to nu. And minus the mu nu. Derivative with respect to sigma. Okay, and here I have everything. And as I said, I make a summation of all this with respect to sigma, and sigma goes from 0 to 3. D minus 1 is 3 because the dimension is 4. And here I just make a summation. So this is my gamma, and I can write it that this is gamma mu, nu, and rho. That's it. Okay. Questions? So the summation goes from 0 to 3, because for us we start at 0 of all these things, and with that you get gamma.
So directly we cannot write calculate Christopher symbol in that manner. You have to describe in this manner.
Yes, there is a there is a program which is called GIAN tensor, and then you just write the metric and it gives directly the Christopher symbols, etc. But that program does exactly this actually. Yeah. So when someone wants to work in something which is different than the standard model like GR, then better to do to use your own program, because if you want to do something which is completely different, maybe it will not be possible with the standard program. So then it's better to build your own program from scratch, and you just run it, and it's easier. And with that, we can do perturbations, we can do whatever we want. So then it's pretty simple. So I have to assign a value to mu, nu, and rho. So what I'm going to do is just to put a loop on each of these variables. Mu equal to 0 to d, mu plus plus. So mu will take value 0, 1, 2, 3, make a loop, and it will take all these values. And the same thing for nu. And for rho also. Okay. Now this I can run it, and it made the full loop. And if I calculate, for example, I say I want gamma, notice the indices. The first two indices are the lower indices in my notation. The last one is the upper one. So I say 0, 0, 1, then it's 0. If I say 0, 1, 1, it's a dot over a, etc., etc. So now I made the loop, and it calculates. They are already all calculated. So it assigned the mu and nu and rho value, and it did all the calculations, and I have them all. So in this way, you have all the crystal symbols. I don't have to save it. So far, fine. So then, I'm just going to use the formulas. What is the Riemann tensor? Riemann tensor is just derivatives of this. So let me go back now to this program here. So this is what I said, crystal symbols. So now I just take the Riemann also. You just have to write the formula, what it means. Riemann has 4 indices. And Riemann, what it is, I can then write it. Of course, if you use another book, maybe Riemann doesn't have the same form. But I use the book by Wald, and it says that R, mu, nu, rho, sigma, and then you just copy it, is the derivative with respect to nu of gamma, mu, rho, sigma, minus the derivative with respect to mu, gamma, nu, rho, sigma, plus gamma, and you have some mu, rho, lambda, and gamma, nu, rho, lambda. So with this, we have the Riemann tensor. What it means, again, you have a summation on lambda. So here you have to make a summation on lambda from 0 to 3. So there are 4 terms to calculate. The first thing is that I take my gamma, which is written there, mu, rho, sigma. I make the derivative with respect to nu, and then I say that you should know what it means, minus the second derivative with respect to mu, careful to the indices, plus this, and then the product of one gamma by the other gamma, you make the summation on the index lambda from 0 to 3. I work with general dimension in order for you to do it with any dimension, and minus the other gamma times the other gamma, and you make the summation. And with that, you have the Riemann. You have to assign a value to all values of mu, nu, rho, sigma. Okay, so with that I have the Riemann tensor. If I want to call a Riemann tensor, then for example, this is the Riemann tensor, the 0, 1, 0, 1. And you can calculate any Riemann tensor of this form. Now it's easy to get the other ones. If you want the Ricci tensor, it's just the summation on two indices. Ricci tensor is the summation of these two indices. So you say that Ricci is this is what it is. You make the summation on the second and the last index, and you keep these two free. So doing that, you get the Ricci tensor. So you do it in the same way. You say, okay, I want the Ricci tensor, so I will write it like this for Ricci. And I have something like this equal to the summation of the Riemann tensor. First index is mu. Second, I will make a summation on it. And you make the summation for alpha from 0 to 3. You assign a value to mu nu. And that's it. And with that, you have your Ricci tensor. And now if you want the curvature scalar, R is just G up mu nu just maybe I should define it first for the people who don't know this curvature scalar. The curvature scalar is G mu nu R mu nu. That means that you make a summation on mu from 0 to 3, on nu from 0 to 3. So that is what you have to do. So you take G up, Ricci mu nu, and you make a summation double on both indices from 0 to G minus 1, and you do the same one from 0 to D minus 1. And that's it. And you have all the quantities you want, and you can say what is R now, and it will tell you this is R. If I simplify it a bit, I'm getting this. So this is my curvature scalar, and I can calculate whatever I want with this, okay? And if I don't know if you have questions so far. I can define another quantity, the Einstein thing, just for you, if you have a Windows, maybe it's Control 5 or Command 5 for the ones which have a Mac. It's if you want, no, it's not that. if you want to command 5 or control 5, write some comments. So for example, I will write now that we will write the Einstein tensor. It's just for you to organize a bit things better. So now I will write the Einstein tensor, which is the tensor G mu, which is the Ricci tensor minus 1/2 R G down mu nu. So this is going to be the Einstein tensor. So this will be actually the Einstein tensor, which is Ricci minus 1/2 R G mu nu. So if I do that, I have the Einstein tensor. I can always put a simplify in order for the last form will be simple. So then I can say what is G00, and it says it's this. Means 3h squared in our notations. So with that, now I have directly the first Einstein equation. Einstein says that G mu nu is equal to 8 pi G mu nu. So if I take the 0, 0, I'm getting from Mathematica that this is 3h squared. G00 is the density. So I'm getting the first Riemann equation like this. And if I want to have G11, for example, G11 will be this, and then you replace it again, and you get the second Riemann equation. Why I prefer to work with my own program for this particular reason is that you can always define some new rules. I will call something, I will call it rule. And for example, I would like every time that the program will see a dot to replace it, an arrow means to replace it by this. This is the definition of h, the Hubble function, which is a dot divided by a. So every time you will see an a dot, you will replace it by this, okay? So if I call this, it gives only this. But if I tell to Mathematica, you should know rules, I'm getting 3h squared directly. So I'm getting it in the form I would like, which is more simple for letter things. I can add other rules, like the second derivative. I would like the second derivative. What is the second derivative? It's h squared plus h dot. So for this one, I will get this. Okay, so I'm getting that it is minus 3h squared minus 2h dot times a squared. So in this case, I can really write it in a quite compact way, in the way I want, always by adding some new rules. So the rules are always written this way. This is just a variable equal to something. And there I say to the calculation, you should know. This is what it means. You should know this. So you should know that a dot has to be replaced by that a double dot has to be replaced by that. So then you get a very simple and compact thing. So first, I don't know if you have right now some questions, we can check a simple calculation is Schwarzschild, the Schwarzschild space-time. Or I can even do it more generically. So I'm going back here, and I say, okay, let us take some function f here of r. Here, another function, 1 over fr. So for the people who know about Schwarzschild solution, for a spherically symmetric solution, this is how the metric would look like. But I still don't know what is f. So I keep things like that, and I just want to solve the equations. So for the others, just to explain what it means, is that I have a spherically symmetric problem, and I'm saying that I'm looking for a metric which has this form. So there is this f of r, fr, r squared, etc. And I'm writing my differential equations. I'm in the vacuum, so this is 0. For the black hole solution, we are in the vacuum. So G mu nu is equal to 0, and this means R mu nu equal to 0. So what I want to solve is only this equation, okay? So we do it in the same way. I just change the metric. Now I have my program, so I don't need to write it again. I do this. This will tell me what is G down. I have to change my coordinates. Now I'm working with spherical coordinates. So I have t r theta phi. These things will give something, it doesn't matter. So with that I run gamma. With that I run Riemann. I have Ricci, have the curvature scalar, and here I have the Einstein tensor. So I ask, what is Ricci 0, 0? It's something like that. What is Ricci 1, 1, for example? It's something like that, etc. And I can solve it. Okay. So I solved my differential equation. Solve is when you want to solve an algebraic equation. D is for a differential of the Ricci 1, 1 equal to 0. F is my variable. R is the variable of the function. And I'm getting that the solution is some constant minus another constant divided by R. And this is going to be the Schwarzschild solution. Okay? So the Schwarzschild solution is this. When I have here 1 minus some constant divided by R that I put here. So you can recheck it then. And you can check that everything, if I simplify, should be 0 because it gives 0 at the end. I 0, Einstein tensor, any component of Einstein tensor like the 0, 0 is 0, the 1, 1 is 0, etc. So we have a solution like that. So this is for the background. You just define something like that and you can go with it very easily. Now imagine that we want to do perturbations, which is going to become much more interesting. So let me go back. Now you just change the metric actually. You can do whatever you want with that. You just change the metric. So imagine that you have an initial metric, which is this, and I will add some perturbations. So let me add an additional matrix, which is going to be my perturbation. And I will put a factor epsilon to say that this is going to be a small perturbation of it. So I have a 2 phi. You remember the Newtonian gauge we took yesterday? So this is going to be this.
Can we add the perturbation part in the same matrix?
Sorry?
Can we add the perturbation part in the same matrix also?
Yes, definitively. I just write in this way to make it more clear, but yes, definitively I will write it also in the other way. So either you write it like this, or you just put it here with an epsilon. And it's good that you said that because then I understood that I forgot that I forgot an a squared here. So either you write it in this way or in this way. Yeah. So we don't see it completely on the screen, but this is the metric we looked for yesterday in the Newtonian gauge, which is Minkowski plus some Friedman, sorry, plus some correction, where there was these two scalar potentials, phi and scalar potential psi. These two are different. They don't look very different on this screen, but for me they are different. This is psi, this is phi. Okay, and they are functions of t, x, y, z, of everything. So just to make it clear, I separated both here, and I kept some epsilon. So I run this, and then after that, I run the same things, exactly the same things. I don't have to change anything. My program is made now, and finally the Einstein tensor. Okay, so imagine I want to know G00. G00 is this. It's a bit complicated maybe, not so much actually, but this is the exact solution. There is no approximation here. If I want to make an expansion at the first order, as we said yesterday, so then the good thing is that Mathematica can do it exactly. I'm saying that you have to make a series expansion of the parameter epsilon at around 0 at the first order. So you do that, so now it makes the expansion up to order epsilon squared. And this is what you get. You get, I will just add the rule in order for it to write it in the compact way I like, and you get this. So it tells you that at the first order of perturbations, the G00, so this term here, is just 3h squared plus 6h psi dot. So this is what you have at the first order of perturbations. So then all the calculations we did yesterday, you have them very easily at the order you want. You can calculate the G11 if you want, then you get something. It's much more complicated, but you get it also. So normal is just to kill this thing here. I don't want it anymore to appear, so I'm just removing it by writing a normal. So you get something complicated, but this is what it is. This is the expression. Questions? There are some people who are trying to do it at the same time or not? Did you face some problems? The expression for? It didn't work? Oh. So at the same time I will pass. I'm trying to take a bit more time, because otherwise we almost finish.
Isn't the part of it
For the perturbation.
Yeah. So we can take epsilon is equal to 0 then?
Yes. Mm-hmm. No, here it's 2 x2, 3. x2, x3. No, this one is x1. This is x2 and this is x3. No, it's maybe okay, but just put simplify. Yes, yes. No, this is okay. The Riemann, maybe there was something, I'm not sure. Here you have twice the same index, mu and mu. Yes. Yeah. Okay, run it again. Just this part from the here directly. No, no, it doesn't work yet because you have 2 plus, which is a strange thing. But maybe there is just recheck the indices here. Okay. This program, you will have it also if you want to work with this program. I think it's much better than if you use some sort of black box and you don't understand what the program is really doing. The interesting thing is that you can then work at the level of Lagrangian. Remember what is the Lagrangian of, is the square root of minus g times the curvature scalar. So if I do square root of minus the determinant of the metric times r, this is going to be my Lagrangian for gr only. It's just this square root minus g times r. If I want to add a scalar field, I add a scalar field. It's not a big deal. I will add a scalar field in 1 second, actually. So then you have this, and you can expand it at the order you want in perturbations. You want to expand this at second order of perturbations, you expand it at the second order. And you can say, I want only the second order term, because this expansion has order 0, order 1, order 2. You can say, I want just order 0, so series coefficient, order 2, and here we go. So this is what you have. So then you have something, okay, it's complicated or not, but you have the full expansion at the second order. Now, the additional thing we can do is to add a scalar field. So adding a scalar field, here it's much simpler. So let me see what can we do with a scalar field. For example, you can add a kinetic term. So let me always add a comment. I want to calculate something I don't remember how you write the partial derivative. Yeah. Okay. So here I want to write this kind of terms. The 1/2, the kinetic term for a scalar field. So what I'm going to do, what is the definition again? The definition is simple. So then you can just focus on the physics because the calculations are trivial. You don't have to spend too much time on it. A kinetic term like this is just 1/2 g indices up, d mu phi, d nu phi. Okay, so I will do that. I will take a scalar field. I will suppose that we are in cosmology, so my scalar field depends only on time. So I will consider just a scalar field which depends with respect to time. And I will make the derivative with respect to x mu. And again, I will say you should know all these things, because otherwise. So this is the derivative of the scalar field with respect to mu. I have to do the same thing with respect to nu. Multiply everything by g up mu nu. And make a summation on all these indices. Okay, and is left only the factor 1/2. So with that, I should have this kinetic term. So I will just call it like this. And let me simplify it a bit. And it's what I have. This is with the perturbation. If there was no perturbation, so if I do the expansion of this at the order 0, I will get just the standard kinetic term, which is minus half phi dot squared. But if I want to add perturbation, then the correction will be minus the potential that we had before, phi dot squared. So then the kinetic term comes very easily like this. You can calculate it, okay? Questions on this one? So I'm going to add then an additional term, which is the box of phi. And then maybe I can do the Gauss-Bonnet and prove that the Gauss-Bonnet doesn't contribute, because we were talking about it this morning. So the additional one is this thing, the box phi. Box phi is g mu So what that it means is g mu, it's g mu nu phi minus gamma mu nu sigma g sigma phi. This is the definition of the box. So, same thing. What I have a g up mu nu times what? Times two derivatives of the scalar field with respect to the first one x mu and the second one with respect to x nu. And I put these rules. Okay, so here I have the second derivative minus the gamma, which is mu nu, the sigma, and the derivative of the scalar field with respect to x sigma, and I put the rules here. And I make a summation on the index sigma. And that's it. So this I will call it box. Box phi is this, and I have to make the summation on the indices mu nu. simplify it a bit. Okay, so this is what we have. This is at the order we want. Mathematica calculates it in an exact way. If I want at some order, I just ask for it. At the order 0, it gives this, which is minus phi double dot minus 3h phi dot. But if I want it at the first order, I get that, etc., etc. So then you can calculate whatever you want. You just add this and you make your definition, and that's it actually. Okay, questions? Okay, if not, I'm going to the Gauss-Bonnet. So we talked this morning about some very particular combination. And we said that this is a total derivative. So let's see if this is true or not. Of course, I will not check it generically. I will take a specific metric, which is Riemann, and we will see if it is true or not. This very specific thing is this, minus 4 r mu plus r squared. So this is called Gauss-Bonnet. It's equal to this. Remember that for me, my indices are like this. I have one index here up. Okay. So I'm just going to write this and see if not this, the Gauss-Bonnet, I will call it G. Or I will call it R Gauss-Bonnet. I will call it like that. So I have to prove that square root of minus G times R Gauss-Bonnet is a total derivative. So this is what we are going to try to see, if this is true or not in a specific case. So how to do that? I have to build my Gauss-Bonnet. So first of all, I will start by changing this. This one is okay. This Riemann tensor, I have it, is the Riemann that we are calculating. This one, I don't have it. The indices, these three indices, I have to lower them. This one, I have to put it up. So this thing here, I have to write it as an R mu1, rho 1, sigma 1, G up mu1, G nu 1, G rho 1, G sigma 1. This is an object I have. I multiply it by all these G, make all summation, then I will get the indices at the level I want. Because otherwise it doesn't work. And you see that if you do it by hand, that will be some endless kind of job. So I start with this. I have a G up. Now I just write what is there. G up mu 1. That is the first one. G up nu 1. G up rho 1 and G down sigma 1. Okay, and times the Riemann tensor. So times the Riemann tensor, which is mu1, rho 1, and sigma 1. Okay, so this is the term I did. I just have to make a summation on all the indices which are repeated, which are mu1, u1 rho, and sigma 1. So I have 4 summations. Okay, so with this we have the Riemann with the indices we wanted. So means this Riemann tensor, this Riemann tensor. Now we just multiply it by the other Riemann, and I make summation on mu, nu, rho, and sigma. So the next step is just to take this, multiply it by Riemann, mu, nu, rho, and sigma, and make 4 summations on these indices mu, nu, rho, sigma. Mu, nu, rho, and sigma. Okay. So that gives something. Is the Riemann square. Now, to this, I have to remove 4 times the Ricci squared. So Ricci squared is going to be exactly the same. You have this term here. This one is okay. This one is G mu mu1, G mu mu1, R mu1 mu1. And you make a summation on all repeated indices. So I do the same thing. I have Ricci with indices down, mu nu, and then I have a G up mu mu1, a G up nu nu1, Ricci mu1 nu1, and I make a summation on all the terms I need. Mu nu mu1 and nu1. Okay, so with this we almost finished, and I have just to add r squared. Okay, so this is going to be what I will call Gauss bonnet. Okay, take some time and we got it. So now I just multiply by the determinant of the square root, and let's see if it will work or not. I don't need to look to perturbations now, actually. Okay, so this is what we get. We get that in the Friedman universe, this term is equal to 24. All this is equal to 24 a dot squared a double dot, isn't it? Yes. And this is the derivative respect to time of a dot cube, a times this. Okay. So in fact, it's just the total derivative of something. So in my action, if I make some derivation, some variation of something, this term will never contribute. But it's not only for the space-time. I can take any space-time, and it will be always some derivative, only a total derivative. Here I took Friedman universe. Let me take another space-time, 1 minus the Schwarzschild black hole, which is a space-time which has this form. Then you can prove it exactly. It's an algebraic structure. It is said that it is a topological term. It just tells you about the topology. So this is the Schwarzschild black hole. I run it again, and I just, I have these coordinates, t r theta phi. It's okay. The curvature scalar. This we don't need it. And where is it? Yeah, it's here. The Gauss bonnet. Huh?
In the very process, we actually we lose one equation, is not great man. We lose one equation if we initially pick them.
We lose one equation. Do you mean?
We've got two equations.
Yes.
But here I can get
We get the two equations. One is the 0, 0. The other one is the 1, 1. I'm always getting two equations. So I should not write it. I mean, I can explain that this is just something. It doesn't matter because.
Riemann square.
Huh?
Riemann square. Curvature is scalar.
Yes.
Sin theta will not.
Huh?
Riemann square.
No, the sine theta comes from the square root of minus the determinant. Yes. So it comes from there. Looking at it in this way, it is trivial, of course, but so let me change it a bit. Because I didn't keep any function. In the sense that I'm just getting now of 48 m squared and this is just an integral, so it's something. You integrate over theta, you get something. Over phi, you get 2 pi theta, and you just get something. So of course it's just something. Because I didn't give any freedom, I should call it FR, for example, in order to reassure that it's a total derivative. Otherwise, it's just it's kind of trivial. So let me integrate it again, and you get the Gauss bonnet, and we are left with that. So I have 4 sine theta. Now it's more interesting. So I have 4 sine theta times something. And that something is f prime squared plus 1 minus f double prime. No, minus 1 plus f. F double prime. Okay. So is this the total derivative of something? The integral over theta and phi, etc., it doesn't matter, it gives something. And we are left just with the integral over r. And you get this. And you get only this derivative. So again, it's just a total derivative of something. So you can use it for any space-time, repeat that again and again, and you will see that Gauss-Bonnet is always a total derivative. So just finishing with the Gauss-Bonnet term, this integral, the Riemann squared, it's a very particular combination with minus 4 Ricci squared. It's not any kind of combination, plus r squared. This is always just some sort of surface term because this is a total derivative. It is called a topological term because actually it measures just some part of topology, in the sense like there is the Chern terms, it's the Chern class, which is just measuring some sort of how many holes do you have in your space-time. So that will give you just in some sort an information of the topology of your universe, of your space-time. So that is something equivalent to that. So this is just a total derivative. So that just gives you some number, which is telling you some sort of thing about the full topology. But it doesn't say anything about really the equations of motion or geometry, because this is just some constant. If you make variation of it, it gives 0. When it is not a constant, is that if you are not working 4 dimensions. And many people are working in 5 dimensions in order to get a term like this. And this is related also to string theory and things like that. So people are interested by this Gauss-Bonnet term. But in 4 dimension, it is trivial. Trivial in the sense that it doesn't help in any way the equations of motion. Questions?
Not question, suggestion. Perhaps you should take rest today.
Okay. Now I was trying. Now I was hoping that Sushant will arrive before because he knows Maple, how to use this program which is called GIAN tensor, but it seems that he's not here yet. No.
Tomorrow, what you are going to cover in morning lecture?
So tomorrow I will talk about a second type of theories, which is extra dimensions. So unfortunately, it seems that things are going to be a bit more short. So I'm going to talk about theories in 5 dimensions. In 5 dimensions. So I work in 5 dimensions, and I have something which is called a brain, which is just a surface, which is a 4-dimensional surface. So the first part will be just geometry. How do I embed a surface, a hypersurface, in a higher dimensional space-time? So how do I put this 4-dimensional space in a higher thing? So this will be just the geometry of tomorrow, in the sense that can I always have a 5-dimensional space-time, and in this 5-dimensional space-time put some hypersurface which is 4-dimensional. So I will include actually this in 5D. And we say that Earth will live on this hypersurface only, and there is an extra dimension that we don't see. So first part is about this geometry, how to embed that, etc. We will see that we need to add some extra things. Once we do that, then I will just look to the full thing from only my position, which is here, and I will get some theory, which is where there is again a scalar field. Somehow a scalar field always comes, and the scalar field is actually the position of this brane. If you take some reference here, this is phi equal to 0, the position of the brane here, the position is different than here, etc. So this is phi of x. Is the position of the brane in the higher dimension. And this is called the Galilean field. And this is what I'm going to try to explain tomorrow. And this field comes also with a mechanism in the sense that we explain today why it gives some effects only at large scales and why at small scales it doesn't give any effect. And it's called the Weinstein mechanism. So I will try to see if I have time to explain both, how to, from 5 dimension, reduce to 4 dimension and get what is called Galilean, and how this Weinstein mechanism works, actually. That is going to be the idea of tomorrow.
Means black holes in higher dimension, no?
Black holes in higher dimension, no. Friday I will do black holes, but in 4 dimensions. I can say some words about higher dimensions, but Friday will be black hole, but in 4.
Excuse me, sir. Sir, could you please describe these 5 dimensions? Like,
Maybe 2 more on now, yeah.
5 dimension will be the course of tomorrow, actually.
no, just the basic one, like what are type of, like these are positions or like related to the time?
What is position?
The basic one about these dimensions.
The extra dimension is space dimension.
Like we only know space time, like the
Yeah.
space and the time.
Yeah. So it's an extra space dimension, not time, because otherwise we have 2 time, and that will.
Very confusing.
Exactly. Yeah, there are people who worked on that, but of course what they found at the end is that it's confusing. So
We are not really knowing what is time.
yeah, no, that's true. Yeah, that's true. So the extra dimension will be space, an extra space dimension, just that we don't observe it yet, but it is an extra space dimension. Space is okay. You can add as many space dimensions as you want. Time is tricky.
So could you please give this code? We can-
Yeah, sure. The what? The code?
Yeah.
No, I will send actually all the codes together because I didn't finish the other codes.
Today just I can have practice. Done.
Okay.
Because it's very important.
Okay,
It's very,
but-
very important.
Okay, so let me see which one I can send. Maybe just this one. Hold on, I will don't save and reopen it. Yes, okay.
If you're feeling well, we can have a chat and just small chat.
Yeah, I have to write my notes. That's
You
the
have
only.
finished it.
No, not at all, of course. Not at all.